In this module, we'll look specifically at how to measure flow rate and determine the system's total dynamic head, or TDH. All covers listed to the ASME A112 19.8 2007 or later standard have a published flow rate. This published flow rate is often different for floor and wall mounting. Most health and building codes require a flow meter in public pools, but we also need to confirm that the flow meter is reading accurately.
Historically, there is one other complicating factor. Most pool codes have specified TDH to ensure proper pool turnover. Pool turnover is typically specified in hours. It is the time allowed for the pump to move an amount of water equivalent to one pool volume. Let's say the code requires a 6-hour turn and the pool is 25,000 gallons. To determine the required flow rate, we divide 25,000 gallons by 6 hours, and then we convert hours to minutes by dividing by 60. Here we get 69.4 gallons per minute, or GPM. This is the required turnover to adequately circulate the pool. A pool circulates by continually turning and diluting dirty water with clean water. Our current codes are based on sequential dilution studies by Gage and Bidwell in the 1920s. Here's what they found. At one turn in a 24-hour period, or T equals 1, the pool will be 63% clean. After the second turn in the same time, it will reach 86%. At T equals 3, it will be 95% clean, and T equals 4, it will be 98% clean. T equals 4 is equivalent to a 6-hour turn, or 4 times a day, which is typically found in most health codes. If we take this a little further to 5, 6, or 7 turns, you see that each successive turn has less and less impact on water quality. For example, moving from 6 to 7 turns adds only an additional 0.2% of cleanliness. It is interesting to note that increasing from 99.9% to 99.99% clean requires 10 turns. That is 3 more turns for a pool that is only 0.09% more clean.
Let's take a look at this visually. If this T represents the dirty water in a pool, and we dilute it with equal portions of clean water, you can see that it gets a little cleaner with each successive pour. If we do this repeatedly, you'll see that by the time we get to 6 turns, there's no detectable color left in the glass.
Here we see a pump with a simple circulation system. The impeller in the pump turns to create low pressure in the pump. The atmosphere then pushes the water into the pump, where it is pressurized and returned to the pool. If we take the same pump and place it on different pools, each piping and equipment system will result in a different flow rate from the exact same pump. The difference between these systems will be the total dynamic head, or TDH. This is a measurement of the pool equipment and piping's resistance to flow. Filters, fittings, pipe length, and heaters, anything the water moves through adds to the TDH. How do you measure TDH? Moving back to our pump example, one typically measures the suction side of the pump with a vacuum gauge in inches of mercury. The pressure side is measured with a pressure gauge in pounds per square inch, or PSI. These two measurements capture what is going on for the entire system. Unfortunately, we have to convert these two measurements to feet of water or feet of head to know TDH. If, for example, we read 6 inches of mercury on the system's suction side and 12 psi on the pressure side, we can convert these to feet of water by multiplying the pressure by 2.31 and the vacuum by 1.13. These are added together and result in a system TDH of 34.5 feet of head. Now, what do we do with this number?
As we stated, when installed on different pools, the exact same pump will have different flow rates. Each pool is unique, like a thumbprint, and that signature is captured in the TDH.
A pump curve looks like this. On the vertical axis, we have TDH, and on the horizontal axis, flow in gallons per minute. In order to use this, you would measure the TDH and then locate it on the chart. So, if our TDH is 55, we find 55 on the vertical axis and move over until we intersect the pump curve. Then we move down to read the flow rate. We see that on this pump, a TDH of 55 results in 80 GPM of flow. It's quite easy. If our cover was rated for 100 GPM and we measure 55 TDH, then we would see that 80 GPM is less than the cover rating, and all is well. But what if we go to measure the pool and it turns out to have a TDH of 30 instead of 55? Now, using the exact same pump, our flow rate has increased 30 gallons per minute to 110 GPM, and that cover rated at 100 GPM would not be sufficient.
TDH has the same effect on flow rate as a hill has on the speed of your car. If you're climbing the hill, you can't go as fast, and when you're going down the hill, you pick up speed. Likewise, when TDH is high, there's less flow, and when it's lower, there's much more flow.
TDH is a measurement of the system's resistance to flow. It is the total loss due to piping, equipment, and fittings on both the suction and pressure side of the pump. The problem we see is that many health and building codes specify a fixed TDH, like 50, 55, or 60, and the pools have been designed to meet the minimum turn at that number. So remember that we calculated the 6-hour turnover for a 25,000-gallon pool at 69.4 GPM. Let's look at that again. If the health or building code specifies 55 TDH, and we look at this pump curve, we see that 80 GPM is sufficient to meet the turnover requirement of 69.4 GPM. The problem is, if we measure TDH and it turns out to be only 30, we really have an actual flow rate of 110 GPM, not 80. This is okay for cleanliness and sanitation, which is historically the intent of specifying TDH in a code. But the actual flow rate now exceeds the 100 GPM rating of the cover.
A little extra water is not a problem for circulation, but it can be a problem when sizing the cover. If we use the health or building code's required TDH of 55, or what's posted on the placard, and then the actual measured TDH turns out to be only 30, we will have significantly underestimated flow.
If our cover is rated for 100 GPM, it would pass at the 80 GPM resulting from a measured TDH of 55. But with the 110 GPM flow rate we get when the TDH is only 30, the cover would fail. Many health departments are missing this, and it's a critical mistake.
TDH is fast and easy to measure. There are even gauges that allow direct measurement of TDH on a running pump. Keep in mind that if the impeller has been changed, the pump curve might not be accurate, but knowing the TDH and determining the flow from the pump curve gives you a second opportunity to verify the system's performance.
Finally, let's turn to flow meters. There are many different types of flow meters: pipe mountable, digital, and even some built into the pump circuitry. But they must be installed correctly, serviced, and calibrated if you want to rely on them for safety. Using a flow meter combined with TDH measurement and a pump curve can give you an idea of whether one or the other is reading accurately. Generally, they should predict flow within 10 to 15% of each other. This popular pipe-mounted flow rotometer style is accurate to about 10% of full scale when it's new, clean, and installed correctly. To work properly, most flow meters require straight pipe for at least 10 diameters upstream, with no fittings. Inspect each flow meter for signs of debris or corrosion and replace if it's fouled. For sensitive safety work, you may want to carry a new, calibrated flow meter that can be temporarily swapped out to see if there are differences in measurement. The electronic readout of digital flow meters may make them appear more accurate, but that does not mean they're more accurate. Like flow rotometers, the digital flow meter sensor must be installed with enough straight pipe upstream of the sensor. Again, confirming flow with both a flow meter and TDH pump curve will give you assurance that you have an accurate reading. Never rely on TDH estimations for anything other than planning purposes. TDH estimations are designed to overestimate TDH, and as such, they always underestimate pump flow. You have to verify the system as built if you want to be sure. In summary, you can't size a drain cover without knowing the flow rate. Never use an assumed TDH to calculate flow for safety. These will likely underestimate flow. Flow meters and estimations from measured TDH and a pump curve should provide comparable flow measurements. Check to be sure that a flow meter is installed correctly and that there's no sign of corrosion.
Selecting a proper cover requires that you know the flow rate. Don't take any chances. Once you know the flow rate, finding a suitable cover is much easier.